we have studied patch and its length for a while. Now it's time for us to study the line integral. Okay, so suppose C is the image of an piecewise smooth parametric patch. C is gamma AB is an image where this gamma is a piecewise smooth parametric patch. Okay, and we have a continuous function f defined over C. This C is a subset of Rn. Okay, because gamma map into Rn and C is its image. Therefore, C is a subset of Rn. So our f is defined on the subset of Rn C. This C geometrically is a curve. Okay. Now f is continuous. Then we defined the integral of f along gamma to be this one variable integral. Okay. Now, this is a curve. Take a parametrization. Gamma. So f is a function defined on the curve C. Their composition is here. Okay. Of course, you can also define an integral to be. This also makes sense because the integral on the right hand side, integrand of the integral on the right hand side is a continuous function. Okay, so this also makes sense, but such integral does not enjoy some very good property. For example, if I choose another parametrization of C, then this integral will change. For our this integral defined here, there is some invariance property. This enables us to define this. The invariance property we will prove right now will enable us to define integral over the geometric curve C. The difference is that here we defined the integral of f over the parametric patch. No problem. Okay, but once we prove that it is invariance when we change an parametrization, then we can define a new integral over the geometric curve, not a parametric patch. Okay, I'm sorry, I usually call patch by curves. So the terminology patch is quite strange to me. Okay, now let's let's prove these results. First, we state the lemma. Let eta alpha beta to Rn be a piecewise smooth parametrized patch equivalent to gamma. Equivalent to gamma means that their image is the same. In other words, this eta is another parametrization of C. We already have a parametrization of the C, that is our gamma, but now we choose another parametrization, that is our eta here. Then we also can define the integral of f over eta. The result is that this equals the previous integral over gamma. Okay, this is the result. From this result, we can define the integral of f over c. To be maybe not fx ds, to be the integral of f over any of its parametrization. Okay, here this x is a point in Rn. Of course, this point should located she traveled along the curve C, along the curve. Okay, so so this lemma is quite important. We prove this lemma first. Proof. We only consider the case for simplicity. We consider the case gamma and eta are smooth. For the piecewise smooth case, you can split the curve into finitely many smooth pieces and apply the result. I will not do this here. Okay. Now, so we assume that they are smooth. We only prove this case. So, because eta is equivalent to gamma, there is a strictly increasing continuous function from the domain of definition of eta to the domain of definition of gamma, that is alpha beta to AB, such that eta is the composition of gamma and sigma. Okay. Now, here this sigma is continuous and strictly increasing. So, so I draw a picture. Yes. This is A, B. This is alpha, beta. This is our sigma. And this is our gamma. This is our eta. So for S not in alpha beta, S not in alpha beta, we know that the derivative of gamma at the corresponding point sigma S not in alpha beta, therefore sigma S not is here. Sigma S not is here. So the derivative of gamma at this sigma S not, you might, if you like, you might define it by T naught. Maybe we denote it by T naught. It's not zero. This is not zero. Okay, this is our because gamma is a smooth parametric patch. By definition, the derivative is everywhere non-zero. This is the requirement of the parametric patch. Okay, so this is a vector non-zero. Therefore, there exists some I belonging to 1, 2. At least one of its component is not zero. Gamma I dot T naught is not zero. Okay, at least one I has this property. Gamma dot is a non-zero vector. At least one of its component, say gamma I dot, the derivative of the ith component of gamma is not zero. We might assume that it is positive. The case that negative is similar, so we might assume that it is positive. So by inverse function theorem, gamma I has a local inverse, local C1 inverse. Denoted by gamma I minus near the point, near T0, that is our sigma S0, near this point. So we apply the composition is here. So from the composition, eta is the composition of gamma and sigma. We get eta I is gamma I composition of sigma. So we apply or we can write this eta I s is gamma I sigma s. These are equivalent. The red and the blue are equivalent. So we applied the inverse to both sides here. So gamma I inverse. Gamma I inverse. Now here is the gamma I inverse gamma I. Therefore, this is the right hand side is sigma s. So we deduce that sigma s is gamma I inverse eta I s. So this is smooth or C1 near the point S0. Because eta I is smooth is C1. Eta I as the ith component of the smooth map eta, it is smooth. Okay, and gamma I inverse is the local the C1 local inverse of gamma I. Gamma I is smooth, therefore its local inverse is also smooth by inverse function theorem. Here we use inverse function theorem. Okay, so this proves that sigma is smooth. Sigma is smooth, so we can apply the chain law to the composition. That is eta equal to gamma and sigma. We deduce that the derivative of sigma eta at s is gamma dot sigma s and sigma dot s. For this equality, I remind you to be aware that this is a vector in Rn. This is also a vector in Rn. But the derivative of sigma at s is real numbers. So this is a vector equal to a real number multiplied vector. Okay, this is true for every s in. This equality is true for every s in the interval alpha beta. Now our purpose is to prove that the integral of f along eta and along gamma are equal. This is what we want to prove. So having obtained the smoothness of sigma and in particular obtained this relation of the derivative of eta and gamma, we can obtain our result easily. So let's have a look. This by definition is AB f gamma t, the norm of gamma prime t dt. So change of variable s equal to sigma t. So this becomes f gamma sigma t. Maybe I make something wrong. Sorry. The change of variable is not s equal. It should be t equal to sigma s. Sorry. T equals sigma s. So the gamma t is gamma sigma s, and the gamma prime t is gamma prime sigma s, and then dt is sigma dot s ds. Correspondingly, the interval of integration is corresponding alpha and beta. Then this is alpha beta f eta s. Gamma eta is the composition of gamma and sigma. Okay, therefore gamma sigma s is gamma s, and the norm of sigma dot using our result here. Using the equality at the last line of this page. The derivative of gamma multiplied the derivative of sigma is the derivative of eta. So you take the norm, because here we need the norm, right? We need the norm of gamma dot sigma s. So taking the norm in this vector equality, we obtain that the is precisely gamma dot s. This is precisely gamma. Sorry, not only this. This altogether, this is precisely the norm of this by our last equality in this page. Okay, so so this gives us the norm of eta as ds, but this is precisely eta f. So this proving our theorem. Okay, so up to now we have already introduced the concept of line integral or curve integral. Okay, line integral, integration of the function over a space curve. So once we study this kind of integration, there are many physical applications. Let's consider an example.